it appears that the uranium could be hidden at a nuclear site so secret, so deeply buried that it may be basically reachable with bunker busters.
At this moment, what you are seeing is a mountain in Iran. There are no visible structures, no roads, no vehicles, and no obvious activity. Only 80 meters of solid granite covering the secret Iran spent 25 years and billions of dollars placing underground. Every satellite moving overhead sees stone. Every radar scan detects stone. Yet Israel has found ways to look through that apparent barrier, charting what lies deep within the mountain without drilling into it, crossing Iran's border, or alerting the people working underneath that they are being observed.
Craters are now visible at the Fordow site, Iran's main location for enriching uranium at 60%, indicating the use of ground-penetrating munitions.
By ordinary assumptions about physics, the methods being used to see through solid rock should not seem possible. The mountain that isn't empty. Here is the strange part. A satellite flies overhead and records rock. Radar moves across the terrain and returns an image of rock. Even the clearest human view on the brightest day reveals nothing except rock. To every device ever designed to observe Earth's surface, the mountain appears exactly as it should, a quiet, vacant mountain, with nothing unusual to discover. But approximately 80 meters beneath the location, you are looking at something is operating. Machinery is rotating. Ventilation fans are running. Generators are producing a steady mechanical hum in the darkness. Iran placed the facility inside granite for one specific purpose. Granite is extraordinarily difficult to attack from the air. Hundreds of meters of compact, heavy stone can absorb, redirect, or break apart almost any weapon long before it reaches whatever has been built below. The facility was not concealed through paint netting or visual camouflage. It was protected through the properties of matter itself. The rock was so deep and so strong that the energy behind conventional demolition methods would be exhausted before reaching the target. From an engineering perspective, that was an intelligent decision. However, Iran could not disable a second group of physical laws. That is why this story matters. A facility can be placed behind an entire mountain, but its existence can never be hidden perfectly. Anything operating underground produces evidence. A generator, a ventilation system, or even a person walking across a concrete floor sends a minute signal into the surrounding rock. Those signals are incredibly weak. They are almost indistinguishable from nothing, a faint murmur beneath the overwhelming noise created by the planet itself. But the signals remain present, and as long as the facility is active, they continue. Israel learned how to detect them. Welcome to Grand Structures. This is the story of how the interior of a mountain can be examined from outside, and why Iran's most protected installations were never nearly as invisible as their designers assumed. The central question sounds absurd when spoken plainly. How can someone determine what exists inside a mountain while remaining on the surface? How can it be done without drilling entering the country, or allowing anyone working below to realize that the facility is under observation, not through an infiltrated agent, not through stolen construction plans, not through a defector carrying secret files? Israel's answer involves four entirely different areas of physics operating simultaneously. Each technique exploits a separate weakness in the underground fortress. It is not one vulnerability examined in four different ways. It is four independent vulnerabilities governed by four unrelated laws of nature. The most unsettling part is that every weakness was produced by the same things intended to protect the installation, the stone, the depth, and the quiet. We will examine them individually because every method is more disturbing than the one before it. The rock that broadcasts its own location. The first weakness is something no bunker can avoid. Stone is not truly silent, rock transmits vibration. Place a generator 80 meters underground and it will shake. That movement is unavoidable because a generator is a massive machine filled with rotating components. Every machine of that kind transfers energy into the floor or structure supporting it. The vibration does not remain confined to the room. It spreads through the surrounding stone in all directions as seismic energy. It is the same general type of wave produced by an earthquake, but on an incomparably smaller scale. By the time that wave travels upward through 80 meters of rock and reaches the surface, almost all of its energy has disappeared. The signal can be millions of times weaker than an earthquake. A conventional seismometer cannot easily separate it from the permanent background movement of the Earth. Road traffic, wind-distant building work, and ocean waves striking a coastline thousands of kilometers away all contribute to a constant low-frequency vibration. A single sensor attempting to detect one generator beneath a mountain would hear only that planetary noise. It would detect nothing useful. Israel's solution is not to depend on one sensor. The answer is to use many. An array of highly sensitive seismic instruments can be positioned across the surface above a suspected installation. The sensors are not concentrated in one location. They are distributed in a grid, with each instrument placed at a precisely known distance from the others. At that point, the situation changes. A weak signal reaching several widely separated sensors no longer looks like meaningless noise. It becomes information that can be traced to a location. Follow this carefully, because this is where the mountain itself becomes part of the surveillance system. A vibrating object underground sends waves outward and upward. Those waves reach the sensors at slightly different times. The instrument positioned almost directly above the generator receives the signal first. A second sensor located 50 meters east detects the same wave a fraction of a moment later, because the vibration has traveled a greater distance. Another sensor 100 meters north records it slightly later again. A computer compares these extremely small differences in arrival time across the entire array. It then calculates backward, identifying the underground point from which every signal must have originated. The result is not merely an approximate area, it can be a highly precise position. The principle resembles how a smartphone identifies its location by comparing the timing of signals from multiple satellites. In this case, however, the signals are seismic vibrations. The transmitter is a machine that does not even realize it is transmitting. That is the discovery that should concern the engineers responsible for underground facilities. The mountain does not block seismic detection. The mountain is the material through which seismic detection works. Every machine operating underground uses the surrounding rock to send its coordinates toward the surface. The problem becomes even greater because dense, consistent stone can carry seismic energy more clearly with less scattering and less signal loss. Granite is both dense and relatively uniform. Iran selected granite mountains because granite is extremely resistant to bombing. Yet granite is also one of nature's most effective materials for conducting seismic vibration. The defensive shield became the receiving antenna. By strengthening the fortress with solid rock, the designers also created an enormous medium capable of carrying sound. An analyst studying the data does not see only a dot indicating where a machine is located. Different machines create different vibration patterns. A ventilation fan turning at 60 cycles per second produces a stable, repetitive seismic signature. That pattern differs from the deeper and more irregular rhythm of a diesel generator. Both are different from the sharp, brief impacts created by human footsteps. Those signatures also differ from the continuous low vibration caused by a vehicle moving through an underground passage. A specialist with years of experience can study the output and determine more than the location of the installation. The analyst may be able to describe what is happening inside at that exact moment. Are the ventilation systems operating? How many generators are active? Is a vehicle traveling through the tunnels? Through the rock, the facility continuously describes its own activity whether the people inside want it to or not. This is not merely a theoretical experiment. For decades, seismic networks extending across entire continents have detected classified nuclear tests, conducted thousands of kilometers away. Those systems have identified the explosions, estimated their size, and distinguished them from natural earthquakes. If sensor networks can accomplish that from the other side of the world, consider what a tightly arranged cluster of more advanced instruments could detect only a few hundred meters above a machine operating 16 hours every day. At that distance, the separation is negligible. Compared with the sensitivity of the system, the signal could appear extraordinarily strong. That creates an obvious and uncomfortable question. If the walls are already revealing what is happening, what occurs when the operators switch off every machine and allow the facility to become completely silent? Remember that question because the third detection technique is designed specifically for that situation. Before we continue, one quick request. If the thought of a mountain exposing the machinery buried inside it is the kind of idea that keeps you watching videos at 2 in the morning, please subscribe. Everything we produce on Grand Structures focuses on this exact subject. The concealed engineering beneath parts of the world You believed you already understood. You will also want to return for the second part of this story. That is all. Let us go back to the mountain. The mountain that breathes. The second weakness is another problem no bunker can avoid: heat. Every operating system beneath the surface produces it. Generators become hot. Computers release heat. Human beings generate warmth. Equipment used for uranium enrichment spinning at extreme speeds can become intensely hot. Heat creates a problem that differs from vibration. A machine's vibration disappears when that machine is turned off. But while equipment remains active, the heat cannot simply be removed from existence. Heat is a natural result of operation. Wherever that energy travels, it alters the surrounding environment. That alteration becomes evidence. The obvious argument is that no camera can directly see warmth through 80 meters of stone. That is correct. A standard thermal camera aimed at the mountainside would record only the surface temperature created by sunlight and weather. Heat originating at such a great depth spreads through the rock and weakens long before reaching the surface. If Israeli analysts needed to detect the facility's actual temperature directly, the mountain would defeat them. However, this method does not attempt to see the heat itself. It observes the effects produced by that heat. The sequence is important. An underground installation generates thermal energy. Over weeks and months, a portion of that energy slowly conducts upward through the surrounding rock. The stone above the installation becomes slightly warmer than the untouched rock nearby. The difference may be only a tiny fraction of 1 degree. Warmer rock behaves differently from colder rock. It expands. The expansion is extremely small. The ground above the facility may rise by only a fraction of a millimeter. No person could see it. No ordinary photograph would reveal it. A normal sensor would overlook it completely. It is a piece of mountainside moving upward by less than the thickness of a fingernail, and doing so gradually over a period of months. That cannot be photographed in the conventional sense, but it can be measured through synthetic aperture radar. A satellite transmits radar pulses toward Earth and calculates with astonishing accuracy the time required for each pulse to return. The satellite can scan the same area from the same orbital position weeks or months later. When the two measurements are aligned and compared, the system can identify a change in elevation smaller than 1 millimeter. From hundreds of kilometers above Earth, it can measure the surface rising or falling by less than the width of a grain of rice. When Israeli specialists compare repeated scans of a location under observation, a recognizable pattern can emerge. The rock immediately above an active underground installation may develop a stable, gradual uplift, not visible in the nearby landscape. That swelling results from the thermal expansion of stone positioned above a hidden heat source. The mountain appears to breathe. It rises by a minute amount, and orbital radar records that motion over time. The technique becomes even more powerful because the pattern of swelling corresponds to the structure and activity of the installation below. The deformation is not arbitrary. The surface rises most above areas producing the greatest quantity of heat. It rises less above sections that are empty, inactive, or cold. The boundaries of that uplift where the movement is greatest and where it gradually disappears begin to trace the functional outline of the underground facility across the mountainside. A large operating chamber produces a broad area of swelling. A section without power leaves little or no visible deformation. After months of repeated observations, the mountain effectively creates a thermal diagram of its own interior across its outer surface. The motion is too small for human vision, but too consistent to remain hidden. The unforgiving advantage of this technique is that it improves with time. One radar scan may reveal almost nothing. Israel does not depend on a single scan. Analysts layer one image over another building, a record that extends across many months. Random disturbances gradually cancel each other out. The remaining feature is the slow and persistent uplift above machinery that continues to operate. Weather conditions change, seasons pass, surface moisture comes and goes. The gradual swelling above an active underground heat source remains in the same location. Time does not weaken this method. Time is the instrument that makes it effective. Identifying the location is not even its most valuable benefit. The most important advantage is that the technique reveals whether statements about the facility are true. An operating installation creates heat and the stone above it expands. A genuinely inactive installation cools and the surface gradually returns toward its earlier position. By measuring expansion and contraction across time, analysts can determine whether a site is functioning or dormant, regardless of what officials publicly claim. That distinction is essential. Fordow, the facility buried inside a mountain near Culm, remained one of the most closely observed areas on Earth for years. It was monitored continuously from orbit. Therefore, when Iran issued public statements about the condition or activity of its nuclear program, those statements were not evaluated without evidence. They were compared with a location whose surface had already been scanned, measured, and analyzed repeatedly over a long period. In June 2025, Fordow was directly attacked, together with other Iranian nuclear installations, during a coordinated series of strikes. A site intended to remain invisible had already been monitored in enough detail to be targeted accurately. The mountain designed to protect the secret had been providing information about itself for years. However, there is still a limitation. Vibration detection depends upon operating machines. Thermal expansion also depends upon operating equipment. A facility that becomes entirely inactive with no electrical power, no generators, and no heat could theoretically disappear from both systems. That leads to the strangest physical principle in this entire story. It is also the principle Iran could not neutralize. The weight of empty space. The third weakness may be the most difficult to understand intuitively, so it is worth stating clearly and slowly. Empty space has less weight than rock. The difference is incredibly small, but instruments on the surface can measure it. Begin with a fact that most people accept without considering it carefully. Gravity is not precisely identical at every point on Earth. We normally describe gravity as a fixed force with a constant value, but the actual strength of the gravitational pull varies slightly from place to place. At any particular location, it depends in part on how much mass exists underneath. Stand above an enormous body of dense stone, and gravity pulls downward with marginally greater strength. Stand above a deep region filled with material of lower density, and the pull becomes marginally weaker. No human being could feel those variations. Nevertheless, the differences exist and can be measured. Now, imagine carving a tunnel into the granite. Solid granite contains a large amount of mass. A tunnel is a volume where that mass has been removed and replaced primarily by air. Compared with stone, air contributes almost no mass. A gravity instrument positioned directly above the tunnel therefore records a slightly weaker gravitational pull than an identical instrument positioned over uninterrupted rock. There is simply less material below it. In the most literal sense, the empty region weighs less. For most of human history, this idea was scientifically valid but practically useless. The difference was hidden beneath environmental and instrumental noise. Gravity meters existed, but they were not sensitive enough to identify one underground tunnel against the much larger background signal. The effect was real, yet it could not be detected. For practical purposes, that meant it might as well not have existed. Then quantum gravimeters were developed. They transformed the meaning of the word undetectable. A quantum gravimeter determines gravity by observing individual atoms. Lasers cool a small cloud of atoms until the particles are almost motionless, reaching temperatures below those found in deep space. The atoms are then allowed to fall inside a vacuum chamber. The instrument measures their rate of descent with exceptional precision. The speed at which an atom falls is governed by the gravitational field beneath it. By applying laser pulses at precisely controlled moments, the gravimeter measures that fall with accuracy that seems almost impossible. In principle, the device can be sensitive enough for a surface instrument to detect the weak gravitational shadow created by an empty tunnel many meters underground. This creates an enormous problem for anyone attempting to hide a bunker. The method requires nothing from the facility. Absolutely nothing. There is no need for vibration thermal output, radiation, electrical activity, or active machinery. Seismic detection requires generators or other equipment to operate. Radar analysis depends on heat moving through the stone. Gravity mapping depends on neither. The operators could switch off every light, remove every worker, stop every generator, shut every door, and leave the installation in complete silence. A quantum gravimeter passing over the area could theoretically continue to trace the tunnels and rooms beneath the surface. The reason is simple. The empty spaces remain where they are. A cavity always contains less mass than solid granite. That physical law cannot be disabled. It cannot be switched off. And silence provides no protection because the instrument was never attempting to hear anything. This is not entirely speculative science. Gravity surveys have already been used at the surface to locate underground voids, abandoned mines, hidden chambers, and naturally occurring cavities. They work by detecting the slight reduction in local gravity created by the missing mass. Quantum technology advances the same principle to a degree of sensitivity earlier engineers could scarcely imagine. Instead of relying on fine mechanical springs, the instrument uses the behavior of individual atoms. Atoms do not experience mechanical wear. They do not drift in the same way as conventional components. Their behavior is far less vulnerable to changes in temperature. Direct such a device toward a mountain, and it performs the measurement an underground installation cannot prevent. It detects where the stone has been removed. This method permanently defeats the strategy of shutting down to avoid surveillance. Almost every countermeasure imagined by bunker designers assumes that the facility is releasing some signal that an adversary must detect while the signal is active. Stop the signal, the logic suggests, and the facility disappears. But a hole cannot be switched off. At 3 in the morning, with every machine cold and every employee gone, a tunnel remains a tunnel. The atoms falling within the gravimeter's vacuum chamber do not care whether the facility is crowded with workers or completely abandoned. They respond only to the fact that solid rock is missing. At that point, the entire concept of underground invisibility begins to collapse. Seismic analysis reveals what machinery is operating. Radar analysis identifies where heat is being produced. Gravity measurements reveal the three-dimensional geometry of the chamber's tunnels and other empty spaces cut into the mountain, regardless of whether any equipment is active. When the information is combined, the result is not a vague mark on a map. It can become a structural model detailed enough to distinguish separate chambers. There is still a fourth technique. It focuses on the one requirement no underground installation can eliminate, and the one connection no bunker can completely sever. Every underground facility on Earth shares one unavoidable weakness. That weakness is not an exotic quantum effect. It is the need to breathe. Human beings require oxygen. Machinery requires cooling. The air inside the underground complex must enter from somewhere, circulate through the facility, and leave again. Therefore, the supposedly sealed fortress cannot actually remain sealed. At some point, it must connect to the surface through a ventilation system. Whenever air moves, heat moves with it. Air exhausted from an underground installation is warmer than the surrounding external air. There is no practical way to avoid that result. The facility produces heat, and the ventilation network is specifically designed to remove it. Cooler air is drawn inside. Warmer used air is forced outward. At the exhaust openings where the ventilation passages reach the surface, the escaping air is measurably warmer than the nearby stone. Satellites have been designed to detect exactly that kind of difference. High-resolution infrared systems operating from orbit can recognize variations in ground temperature as small as 1/10 of a degree. A ventilation outlet releasing air 3 degrees warmer than the surrounding rock would not appear as a minor irregularity to such an instrument. It would resemble a bright signal against a dark background, a constant thermal marker continuing hour after hour. The harsh reality is that ventilation cannot be removed from the design. It is not an optional convenience that engineers can sacrifice for greater secrecy. It separates a functional underground workplace from a sealed burial chamber. Without ventilation, the workers below would eventually suffocate. With ventilation, the installation exposes itself to infrared satellites passing above. There is no configuration in which the facility can support breathing human beings while remaining completely thermally invisible. Those requirements directly contradict one another. Biology ultimately wins. Iran recognized the vulnerability and attempted to reduce it. Ventilation openings were concealed inside natural cracks in the stone. Some were covered with loose material or shaped to resemble ordinary parts of the landscape. Those measures were not useless. They did reduce the strength of the infrared signature, but they could not remove it entirely. A natural crack does not normally release a steady current of warm air. The pattern created as that heat spreads across the nearby surface has a distinct shape. Its consistency is also unnatural. Ordinary geology does not produce an opening that exhales warm air continuously at the same rate throughout the day and night. With sufficient image resolution, the artificial pattern separates itself from the natural terrain. At that stage, the different detection systems begin reinforcing one another. The ventilation fans pushing hot air toward the surface rotate at measurable mechanical frequencies. That means the same fans appear in the seismic data as recognizable vibration signatures. The one system the installation cannot survive without therefore betrays the bunker in 3 separate ways. It releases warmth that infrared satellites can observe. Its machinery generates a seismic signal that surface instruments can locate. Its continued operation confirms that the installation remains active. The breathing system of the fortress becomes its clearest admission. Engineering cannot fully solve this contradiction. Reducing the size of the ventilation outlets makes the air emerge faster and at a higher temperature, potentially making the signature easier to detect. Distributing the exhaust among a larger number of outlets gives observers more positions to compare and triangulate. Cooling the exhaust before releasing it requires additional energy. That cooling process creates more heat somewhere else, which radar analysis may detect through surface deformation. Every attempt to solve the ventilation problem produces another observable effect elsewhere on the mountain. The air must circulate. Any significant movement of air leaves evidence. Consider what has happened at this point. Every individual detection method seems to have a possible countermeasure. The operators might stop the machinery delay activity until satellites have passed or hide the ventilation openings. But avoiding one form of detection drives the facility directly toward another. Now, observe what happens when Israel does not operate the 4 techniques independently, but uses them as one integrated system. When all 4 work together. Step back and examine the complete arrangement. No individual method explains the entire story. The real power comes from operating all 4 simultaneously. There are 4 independent detection systems. Each relies on a separate law of physics. Each exploits a weakness the facility cannot completely eliminate. Seismic arrays detect what is functioning inside. They recognize generators, ventilation fans, and vehicles by interpreting vibrations that the surrounding stone transmits regardless of the facility's intentions. Synthetic aperture radar identifies where thermal energy is being produced. It measures millimeter-scale movement at the surface, revealing which underground sections are active and which areas have cooled. Quantum gravimeters map the physical layout itself. They detect the tunnels, chambers, and cavities through the lower mass of empty space, even if every system inside has been switched off. Infrared satellites search for ventilation exhaust. They identify the breathing points that no occupied underground facility can remove. Each technique has a limitation when used alone. Seismic monitoring works best when machinery is active. Radar requires repeated observations over weeks or months before a stable pattern becomes visible. Gravimetry generally requires the sensor to pass relatively close to the target. Infrared detection depends on the ventilation system releasing warm air. Any one system may be partially defeated, delayed, camouflaged, or dismissed as ambiguous. But the 4 methods do not remain isolated. They validate and correct one another. A weakness in one technique is covered by the strength of another. Shut down the installation to avoid seismic detection and thermal radar analysis, and the gravimeter can still identify the geometry of the empty underground spaces. Disguise the ventilation exits to reduce the infrared pattern, and seismic instruments may still recognize the operating fans. Radar may also continue measuring the heat generated below. There is no single action capable of closing all 4 forms of observation at once. The reason is that each system detects a different unrelated characteristic of the same structure. The term for this approach is layered detection. Its effectiveness is almost philosophical. One instrument can be deceived because it understands only one feature of reality. Prevent it from observing that feature, and the instrument becomes blind. But 4 systems, each measuring a completely different property of matter, cannot all be defeated through the same trick. No single countermeasure can simultaneously change vibration, heat mass, and airflow in the same way. To defeat the combined system, engineers would need to construct a facility that produces no movement releases, no heat removes, no stone, and requires no air. That would mean constructing a facility that does not exist. This is the most unforgiving irony in the entire situation. Iran was not careless. The people responsible for the nuclear program were not ignoring obvious engineering principles. They spent 25 years and vast financial resources perfecting the concealment. Against the threat they expected, they were largely successful. The weakness was not poor construction. The weakness was that they were preparing to resist a bomb while the actual intruder was a collection of physical laws. Physical laws cannot be blocked by walls destroyed by missiles or changed through negotiation. Engineers can dig farther underground. They can add more reinforcement. They cannot prevent rock from carrying vibration. They cannot stop heat from spreading upward. They cannot force an empty tunnel to possess the same mass as solid granite. Those are not ordinary security vulnerabilities with conventional security solutions. They are fundamental properties of the universe. Israel learned how to interpret them. That is the quiet and unsettling truth at the center of this story. Iran spent years and billions of dollars excavating deeper in an attempt to avoid observation. The installations were moved underground exactly as intended. Israel still found them. It was not necessarily through a spy or an informant. It was through physics. It was through seismic energy transmitted by granite, a material that carries vibration exceptionally well. It was through rock rising and falling by a fraction of a millimeter above underground heat. It was through the measurable absence of mass created by empty tunnels and detected through falling atoms. It was through warm air escaping from ventilation outlets disguised as natural stone. The fortress became the source of the evidence used against it. Return now to the mountain where the story began. Fordow was constructed to withstand attack. It had approximately 80 meters of granite overhead, heavy blast doors, and multiple layers of emergency power. It represented some of the most heavily reinforced military engineering in the region. Many people described it as indestructible. Within a limited engineering definition, that description was not entirely false. Delivering a weapon deep enough to reach the facility was an enormous challenge. However, beneath the question of whether a bomb could penetrate the mountain was another question that had to be answered first. It was equally important, yet received far less attention. Before deciding whether a target can be destroyed, someone must first determine whether the target can be found. Can its internal structure be reconstructed? Can its actual operational condition be monitored from outside, perhaps even in near real time, without the people below realizing that information is being collected? Consider what that means for the engineers who designed the site. According to the traditional logic of bunker construction, they made the correct decisions. They dug farther down than most observers believed necessary. They selected the strongest available stone. They reinforced the access points. They duplicated critical power systems. They buried the entire operation beneath a mountain that most ordinary weapons could not penetrate. Every choice made sense if the only threat being considered was a bomb descending from the sky. But the most important threat was not initially the bomb. The greater threat was observation. Against observation, every apparently intelligent engineering choice began working in the opposite direction. Greater depth meant more stone through which vibrations could travel. Harder and more uniform rock produced cleaner seismic transmission. Additional equipment generated more heat. Larger facilities required more tunnels and chambers, creating a stronger gravitational signature. The fortress had been optimized against the wrong opponent. Physics cannot be used as a hiding place without consequences. Rock may block direct access, but it also carries seismic waves. Stone expands when heated. Solid rock has mass that an empty tunnel lacks. Warm air escapes wherever ventilation passages connect the bunker to the outside atmosphere. The same qualities that made granite an excellent protective barrier also made it an effective source of information. The mountain selected by Iran to guard its secret became a continuous and highly detailed witness against it. It provided the evidence silently and visibly and at every hour of the day. Knowing the location of the bunker and understanding what is operating inside solves only one half of the problem. It may even be the easier half. A far more difficult question remains. After mapping a target 80 meters beneath solid granite, how can it actually be destroyed with a conventional weapon? In Part 2, we will examine the GBU-57 massive ordnance penetrator in complete engineering detail. We will explore how it forces its way through solid rock rather than breaking apart at the moment of impact. We will examine how the weapon identifies the number of layers it has passed through and determines the correct instant to detonate underground instead of exploding at the surface. We will also explain why the effort to create an invulnerable bunker and the effort to design a weapon capable of defeating it have remained locked in a 30-year competition that neither side has conclusively won. Subscribe to us so that Part 2 appears for you as soon as it is released. Before leaving, consider one final question. People remain sharply divided over the answer. Now that you understand how underground installations reveal their presence, do you believe a genuinely undetectable subterranean facility can still be constructed, or have the laws of physics quietly made the perfect bunker permanently impossible? Share your opinion in the comments. Part 2 is coming, and after watching it, you may never look at a mountain on a map in the same way again.